Hello everyone. Today we'll be seeing some basics of testing of hypothesis. First of all, what is meant by testing of hypothesis and when do we need it? Okay. So we all know that statistics is useful when you want to conclude on the basis of sample something about the population. So what I have is some big population. I'm interested in studying some characteristic of this population and I study a small subset of that population which is a sample. So on the basis of this data, we want to generalize and conclude something about all these individuals, right? So when does testing come in picture? In this same thing, testing comes in picture. Why? Because let us say that for example, recently there was an exercise to see how many Puneites have developed antibodies for say COVID-19. Okay, so the newspaper report said that around 50% or 57% something was a number, people have already developed antibodies. Now this is suppose entire population from Pune city, so they had taken some people from some pockets, right? 5 different wards I think. So out of these people, in fact not everyone from these wards were also surveyed. There was a certain subset of these wards which was surveyed. So out of these people, suppose 57% people showed antibodies. Then of course, yes, if your sample is fairly representative, then we can say that okay, overall in the entire population also roughly 57% would have antibodies. But roughly means how close to 57%? So if 57% is here, 50% is let's say here. So can I say that okay, at least 50% of the people from entire Pune have developed antibodies with say some confidence? Means I might be interested in suggesting something like this, that at least 50%, so more than 50% people have developed say antibodies. So this is my interest. So this is called as my hypothesis of interest. I am interested in concluding something like this, that yes, at least 50% people. So number of people or the proportion of people who have developed antibodies is more than half. Now this hypothesis of interest is also known as research hypothesis. Okay. So if we want to prove this, what should I do? Now this we are saying is about entire Pune city. Okay, we are not saying now just for this sample, because in this sample it is already more than 57%, but our interest is in entire Pune city. Now remember, disproving something is generally easier than proving something. Okay, for example, we have always heard, all crows are black, all crows are black and so on. But can you actually prove that all crows are black? If you want to do that, what you would have to do? You would have to check each and every crow in the entire world and see whether all of them are black. Because even if you can find single non-black crow, then you're done. I mean, your hypothesis gets disproved. So disproving is easier because for disproving even single instance is fine, whereas for proving you have to prove that each and every crow that you come across, not just that you come across, each and every crow that exists in the world is black. So disproving is easier. This is taken into consideration while testing of hypothesis. So what we do is, generally whatever we are interested in is this. So but as I said, proving this is easier. So what we do is we take complement of this and try to disprove it. Okay, so there are two major concepts in testing of hypothesis. There is something called as null hypothesis and something called as alternative hypothesis. So as I said, proving is difficult. So proving that P is greater than 0.5 is difficult. So what we try to do is we disprove the complement of it. Okay, so that's why generally the research hypothesis or the hypothesis of interest, research hypothesis or the hypothesis of interest is taken as the alternative hypothesis, and generally complement of that is taken as null hypothesis. So for example, here my null hypothesis would be P less than or equal to 0.5 and alternative is P greater than 0.5. Okay. So if P is less than or equal to 0.5 can be disproved, if this can be disproved, then we would say that yes, there is not enough evidence for this, so I would support this. Okay. So I can say that there is enough evidence against this, so I would support this. Okay. So you have to always remember whatever is of interest is generally research hypothesis, and it is generally taken as alternative hypothesis and not the null hypothesis. Now why the name null? The name is null because generally null hypothesis is hypothesis of no difference. Generally I am saying, okay, not always. What do I mean by this? Suppose there are two drugs in the market, let's say drug A and drug B, and I want to check whether one drug is more efficient than other. Okay. Then my H0 would be that both the drugs are equally efficient. So efficiency of drug 1 is same as efficiency of drug 2. And my alternative hypothesis would be efficiency of drug A is not same as efficiency of drug B. Okay. So again, what we are saying is there is no difference in the drug becomes my null hypothesis. Hence the name null. That generally whenever you have no difference case, it goes under H0. No difference or no change, etc. Okay. It doesn't have to be comparison. Even in the single thing, it can still be hypothesis of no difference. For example, I am talking about single drug only. Okay, let us say I am talking about drug for reducing blood pressure. Okay, now I want to claim, of course, that my drug is effective in reducing blood pressure. So what I would say, that average blood pressure after the use of drug has reduced, so is less than before the use of drug. Okay, so even though I have single drug, hypothesis of no difference still works, because no difference would mean that before and after averages are matching. Okay, so average values of blood pressure before and average values of blood pressure after are matching. That would become my hypothesis of no difference or so-called null hypothesis. Okay. Now as I said, proving alternative hypothesis is difficult. So what we try to do is we try to find evidence against the null hypothesis. If we can do that, if we can collect enough evidence against null hypothesis, then we conclude that yes, alternative hypothesis is probably true. Okay. So what do I mean by finding enough evidence? Okay. Let us say I am manufacturing toothpastes. Okay. So I am manufacturing some toothpastes and there are people who are buying my toothpastes, and I am manufacturing toothpaste and my pack size is 100 grams. So every toothpaste I am saying is of 100 grams. So the quantity in each toothpaste is 100 grams. That is my claim. Now some of my customers suspect that I am cheating in weight. So they feel that the average amount of toothpaste in the toothpaste that they are buying is not 100 grams. Of course, so you go to court. Okay, so you go to court and you claim that this person is cheating and the toothpastes don't really have 100 grams of toothpaste in it. Now court is not going to listen to single person. Court is going to say, okay, produce enough evidence. So suppose you buy, let us say 500 toothpastes, okay, and you meticulously record weight of toothpaste in each of them. So suppose first is 98 grams, next was 99 grams, then third is say 97 grams, some is 103 grams, 100 grams and so on. Okay, weight may not be exactly 100, there of course is going to be some variation. So suppose these are the readings. Now suppose the average reading turns out to be 99.5. Now can you just start celebrating that yes, we have proved that the manufacturer was cheating, he or she was claiming 100 grams and now the weight is only 99.5 grams. The court is not going to let you celebrate it so fast, because this 99.5 is on the basis of 500 toothpastes that you secured. There may be some other toothpastes out there whose average weight may be more than 100. Okay, suppose I simply consider these two toothpastes, then average of these two toothpastes is 101.5. So I can say that, see, there are some toothpastes whose average is more than 100, whereas you are saying there are some toothpastes whose average is less than 100. So both of us can be right or both of us can be wrong. Okay. So in this situation, we need testing of hypothesis. So what statistics tells us is, okay, I have 500 toothpastes, I have data on all 500 toothpastes, and from that I have recorded this as a probable value. Okay, so 99.5 is a probable value, but is this variation due to chance or is it a serious variation? Okay, so what we do is we construct some sort of test to decide whether this difference is significant enough to conclude that it has not occurred due to chance. Okay, what do I mean by occurring by chance? If you take another sample, would you still get, are you still more likely to get values less than 100 than values say equal to 100 or greater than 100? If that is the case, then only you can say that yes, the person, the manufacturer is cheating. Okay, so your H0 becomes, my claim is the average weight is 100 grams and alternative is average weight is strictly less than 100. Okay, so of course, what does it mean? That the test statistic has to be based on difference between this observed value and claimed value. Okay, so it would be based on difference between observed value and claimed value, and you need some sort of normalizing factor or scaling factor to account for variation. Okay, so this change of 0.5 grams, it has to be taken kind of as a relative change. Okay, so if values are very close to each other, then even this small difference is to be considered as significant. But if these values are not very close to each other, means if they generally differ by like say 5 or 6 grams, then this 0.5 grams difference is not significant. Okay, so we need some sort of variation or scaling factor in the denominator, and that becomes my test statistic. Now, who decides what is too large? So I am saying here, okay, difference of 0.5. Is this difference of 0.5 significantly? Is this difference of 0.5 significantly large? So who decides this significance? That significance is decided by sample and the statistical theory. So people have developed theories which will tell you at what point the difference becomes significantly large. Okay, so at what point you should really conclude that yes, there is enough evidence against this and hence this should be correct. Okay, so there are statistical theories to do that. So how is it achieved? One of the commonly used distribution for that is the normal distribution that we studied. The normal distribution is a bell-shaped curve, we know. So ideally, the difference between the observed value of mean, that is x bar, and 100 should be 0 divided by some sort of scaling, I said. Okay, ideally it should be 0. Okay, if your null hypothesis is true. Okay, so under H naught means if your null hypothesis is true, then ideally that value should be 0. Now we are saying that x bar, your claim is that x bar minus 100 is generally going to be negative. That's what the customers are claiming, right? So values near this negative end, they are going to support H1. Okay, if you have large negative deviation, that is going to support the alternative hypothesis that yes, for most of the sample, average value is going to be less than 100. So what we do is, we divide these values into two parts. So let us say this is my kind of threshold. So this part would be called as acceptance region and this part would be called as rejection region. So acceptance and rejection of what? Acceptance and rejection of H naught. So if you have difference to be positive, then of course you are going to support the null hypothesis that yes, that average weight is 100 or even more than 100. If your difference is negative, still up to some values it may be acceptable that okay, by chance I got negative, because even when the mean is 0, means mean difference is 0, ideal scenario, some values are going to lie here and there because you are not going to get perfect 100 every time. So sum means how much, that is decided by this division between acceptance and rejection region. So if it is below a threshold, we say that we reject H naught because this is very less probable. If you remember, height of this curve kind of denotes a scaled version of probability. So as the height goes on decreasing, so under H naught means if the difference between 100 and sample mean is actually 0, then getting sample with such a low value, such a low means very highly negative value, is quite unlikely. Okay, the probability in the height is very less. This is quite unlikely. So we would say that if H naught were true, then this event has very less probability of happening. Which event? That x bar being very small compared to 100. So if H naught is true, then this event has very low probability of happening, and still it is happening in our sample, it means that H naught is probably false. Okay, so values lying in this region don't support H naught, and hence this is called as rejection region. Okay, so if a value lies in this region, you are going to reject H naught, whereas if a value lies in this region, you are going to accept H naught. Now this location of rejection region depends on the sample, depends on the hypothesis. So here, because I wanted x bar to be less than 100 to get rejection, rejection region is to the left. On the other hand, you are interested in claiming that average temperature in Pune for the past, for the month of May for the past years has always been greater than 40. This is your claim, that average temperature is greater than 40. In such cases, if you take x bar minus 40, you expect this value to be large than 0 for H naught to be rejected. So in that case, this side becomes the rejection region. Okay, and this side becomes the acceptance region. Sometimes you may have two-sided hypothesis. So you want to claim, say, theta not equal to something. In that case, you can have rejection region on both the sides. So this will also be rejection region, this will also be rejection region, and this becomes the acceptance region. Okay, so depending on the hypothesis of interest, you decide what is your acceptance region and what is the rejection region. Now there is concept called as test statistic. Okay, so what is test statistic? So here in this particular example, test statistic can be the actual observed x bar minus mu naught divided by standard error of x bar. What is standard error? Standard error is nothing but standard deviation. Do you remember what standard deviation is? Standard deviation is square root of the variance. Okay. So this can be one possible value of test statistic. So test statistic is generally such type of quantity from which we can get some idea, means if the values of this are too large or too small, then we are going to reject. Okay, it doesn't have to be absolute, it can be just the actual difference. Okay, and the graph we drew here, the bell shaped curve, these are actually probability distributions of the test statistic under the null hypothesis. What do I mean by under the null hypothesis? That is, if the null hypothesis is true, then this is the distribution of the test statistic. So test statistic is supposed to have this sort of distribution if null hypothesis is true. And hence we say that okay, values in certain range are very unlikely to occur if the null hypothesis is true, and hence we would call that as a rejection region, and we would reject the null hypothesis if the value of the test statistic falls in that region. Okay. There is another important concept called p-value. Whenever you carry out testing of hypothesis business via software, you get something called as p-value. What is p-value? P-value is of course some sort of probability. So it is probability of getting an outcome as bad or worse than the current sample if H0 were true. Okay, I know this is slightly difficult to digest, so again let me try to explain with the help of a diagram. So we know that this is suppose distribution of the test statistic, and we said that we have say acceptance region here and rejection region here. Suppose for my current sample, the value of the test statistic that we computed, so x bar minus mu naught upon standard deviation of x bar. Suppose for the current sample that value is this. Okay. Now, if H0 were true, then what is the probability that I would get something as bad as this or worse than this? So when I say worse, I mean against H0. So I mean in the rejection region. So this is current thing, and worse than that would mean this region. So entire probability of this region means probability of the test statistic value lying below this value would become my p-value. Okay, if this is my rejection region. On the other hand, if my rejection region was here, then and suppose this is the actual value, then here worse would mean on this side. Okay. Now, what if my rejection region is on the both sides? So if I am having rejection region here and acceptance region here, and suppose my observed value is somewhere here, then what we do is we consider this part and an equivalent part here. Okay, so a mirror image of that, and then we add probabilities of both these, and that becomes my p-value. Now, p-value in this diagram, what I did was I have always placed my observed value in the rejection region, but that need not be the case. Suppose this is my rejection region, this is my acceptance region, and observed region is here, observed value is here. Then in that case, p-value would be this entire probability. So rejection region plus this additional thing. Okay. If my rejection region was here and observed value was somewhere here, then my p-value becomes probability of this part. Okay. And if suppose my rejection region is on both the sides, so this is my rejection region, this is my rejection region, and my observed value is here, then I take this probability and plus add again the mirror image of it from here, and it becomes the p-value. Okay. Now what does p-value tell me? What do the observed rejected values tell me, and so on? So as we saw, in every curve I would have some cutoff or threshold kind of value which would tell me what is acceptance region and what is rejection region. Okay, so this threshold is known as tabulated value of the test statistic. So how do we decide this tabulated value of the test statistic? For that, we need to introduce two new concepts called as type 1 error and type 2 error in testing of hypothesis. So type 1 error and type 2 error. Okay. So what are these two types of errors? So there are two possibilities. H0 is actually true, but we end up rejecting it accidentally. And the other possibility is H0 is actually false, but we end up accepting it, so or not rejecting it. Okay, so these are two types of errors. This is type 1 error, this is type 2 error. So type 1 error is reject H0 even when it is true. This is known as type 1 error. Okay, and type 2 error is accept H0 even when it is false. So of course we try to minimize the error, right? Ideally we don't want both, we don't want to have any errors. Ideally we would like to give accurate decision. Ideally we choose cutoff in such a way that these errors can be minimized. But the problem is both these errors cannot be minimized simultaneously, because when you try to reduce this error, type 1 error, so reject H0 when it is true, it means you are trying to avoid unnecessary rejections. So you try to decrease probability of rejections, or you try to reduce the size of the rejection region. Now what happens is, because of that, size of the acceptance region increases. So sometimes you end up accepting even when you don't want to accept, and hence type 2 error increases if you try to reduce type 1 error. And it is vice versa. So if you try to reduce type 2 error too much, then type 1 error also increases. So generally what we do is we try to control type 1 error first. So try to put probability of type 1 error below 5%, and then with this condition means, so while keeping the probability of type 1 error less than 5%, we try to decrease probability of type 2 error as far as possible. Okay, so how do we do that? How do we control type 1 error? Because type 1 error is rejecting H0 when it is true, so we know that this is anyway distribution under H0, and we want type 1 error to be less than 5%. So we want probability of this rejection region to be less than 5%. So this cutoff is chosen in such a way that probability of rejection region is 5% and probability of acceptance region is 95%. That is how we choose the cutoff. Why? Because we want to control probability of type 1 error to be less than or at most equal to 5%. Okay. So if my rejection region is divided into two parts, the total probability of the rejection region should be 0.05. Okay. So this gives rise to what is known as tabulated value of the test statistic. So if we consider, suppose, standard normal distribution, we know standard normal means normal 0-1 distribution, and if my rejection region is only one-sided, suppose here, then this minus 1.645 is actually the tabulated value of the test statistic. This is the notation T tab, because this is the point at which I have 5% probability here and 95% probability here. Your homework is, I am assuming all of you have at least soft copy of the Daniel's book. So your homework is check the standard normal tables in Daniel's book. Try to see if you can understand how to read those. And those gives these type of probabilities. Those tables give these type of probabilities. So check whether this value has the property that I mentioned here. That is, left hand side probability for this value is 5% and right side probability is 95%. Okay, if my rejection region is on this side for standard normal, this would be plus 1.645, and if I have to divide my rejection region into two parts, then I need only 2.5% on either side, because total has to be 5. So this becomes minus 1.96 and this becomes plus 1.96 roughly. Okay. So now we know that okay, we are going to reject if my observed value falls in the rejection region. So what we check is, for two-sided rejection region, my observed value or calculated value of the test statistic in mod should be greater than tabulated value of the test statistic. So tabulated means 1.96. Okay. Or if your left hand side rejection region is there, if you have a left hand side rejection region, so then my calculated value of the test statistic should be less than tabulated value of the test statistic. And if you have right side rejection region, then my calculated value of the test statistic should be greater than tabulated value of the test statistic. In such scenarios, we reject H naught. And now this tells me how it is related to p-values. So how it is related to p-values? So if this is my threshold or tabulated value, my calculated value is here somewhere, so I am going to reject if this is my rejection region. Now p-value we know is left side probability of calculated. So p-value is this, probability of this region. What I know is the tabulated value has been chosen in such a way that probability of this region, the red thing, is 5%. So it means that my p-value will be less than 0.05. Correct? Same story happens even if you consider right side rejection region. So observed value, if suppose is here, t calculated, and tabulated value is here, then this total region was 5%. So the actual p-value, which is to the right side of this would be less than 5%. Okay. So the criterion in terms of p-value becomes, if p-value is less than 0.05, we reject H naught. So the criterion in terms of p-value remains same irrespective of whether your rejection region is on left side, right side, or it is divided in two parts. Hence generally it is a preferred criterion. Of course this 5% is not God given. Sometimes depending on the context, people may like to change it to 10% or 1%. It depends on which type of error is more serious for you. So if you consider type 1 error to be less serious, then you may allow up to 10% type 1 error and try to reduce type 2 error more. If you consider type 1 error as more serious, then you may want to reduce type 1 error to 1% and let type 2 error increase slightly. So how do you decide which type of error is more serious? As I said, it depends on the context. So for example, suppose you have developed a portable machine which can test person for, let us say, possible clots in arteries. Okay. So you have a small village where no good doctors are available and you want to test all the senior citizens or all the obese people in that village to see if they have a risk of developing clots or if they have a risk of heart attack basically. So you have developed a portable machine. So what you are going to do is, you go to that village with your portable machine. Your portable machine is not 100% accurate, that you know, but still it does something. So what you do is, you go to that village with the machine, you check people, and if your machine says that the person is alright, then you say okay, you are alright, you can go home. If your machine says that the person is susceptible to heart attack, then you recommend that person further treatment. So you tell that person, go to a city, meet this doctor, and the doctor would guide you how to proceed further. Okay. Now here, which type of error is more serious? If you recommend a healthy person go and see a doctor, it is still okay, because the doctor would actually do fancy tests and would conclude that no, you don't need further treatment. Okay. Whereas if you send home a person who is actually likely to have heart attack, then you are kind of denying that person chance of a treatment and the person may end up dead. Okay. So here one type of error is more serious. Same thing may happen in testing of hypothesis problem. Type 1 error or type 2 error may be more serious. So depending on that, you decide whether you want to control type 1 error at 5%, 10% or 1%. If you have no such clear guidelines, then generally 5% is a recommended choice. Is it okay? Type 1 error and type 2 errors are also known as producer's risk and consumer's risk respectively. To understand that, we can go back to the toothpaste example. So in the toothpaste example, my H0 was that the actual weight, average weight, is greater than or equal to 100. Actually, ideally equal to 100. That was the claim of the producer. And alternative is mu less than 100. Okay. So if type 1 error occurs, means what? Reject H0 even when it is true. So even though the person was actually maintaining this 100, but he was unlucky and the sample turned out to be, 1, where the average weight was pretty less than 100, and the court concluded that yes, you are guilty, you are not filling your toothpaste up to the mark. Then this becomes producer's risk. Because why? Because even though the producer was actually doing his part, he got unlucky and the sample gave evidence against him. On the other hand, if type 2 error is there, means if H0 is actually false, means actually mu is less than 100, but the sample turned out to be lucky for the producer, and the court concluded that no, this sample shows that okay, mu equal to 100 is possible, then it's a consumer's risk, that even though the consumers are actually getting less, they couldn't prove it, and hence it's risk for them. So that's why type 2 error is also called as producer's risk, consumer's risk. Okay, so these are two types of errors in testing of hypothesis. Testing of hypothesis is actually linked to confidence interval also, but as I said, we may not have enough time to discuss all these things and still cover the syllabus, so I won't go to confidence interval right now. Now we would start our actual third semester syllabus with this much background in testing, and then we would come back to confidence interval if we need it. Okay. Now your homework is to think of some examples where such testing would be needed and data can be available. The examples can be from your other subjects also. Okay, or they can be from some general general topics of interest. Okay, thank you.